I do wish we could have class outside today, but I don't. Haven't figured out how to make that happen.
Technology.
Yeah.
You just hold up your iPad.
Maybe we'll talk after class and we'll figure out how to do that. You are right. I could probably send you everything on your devices, but then Wi-Fi. I don't know. So that would be kind of cool, but not really outside.
Yeah, that'd be really awesome, right?
So what before we start off with class, for those who just came in, if you want to try to get in the one extra office hour a week, I'm going to try to set up. This is a list of names. Please make sure to add your name to that before you leave. I will then send out a poll to try to figure out if there is any time throughout the week that might overlap. For instance, those who do not have lab on Monday or Wednesday night, maybe right after class could be a time to have office hours. I don't know. I'm going to try to think of all different times that might work. So I'm going to try to make something that overlaps with the names up there. Make sure your name's on. Second thing, Friends in Medicine seminar is Wednesday, 4 to 5:30. It's going to be about the brain. It's actually going to be two super interesting and cool people. One guy who was in the military for a while and then decided to go into research. And so he studies the brain from a NASA, how does neutron bombardment or radiation affect astronauts' brains? So he has NASA funding for that. So he's a PhD, but he has a very interesting background. Antonio Allen is his name. And then we have Annalisa, I think Rodriguez is her last name. She's an MD PhD, and she is a neurosurgeon, and she studies brain cancer. And so the two of them collaborate a lot on studying the brain because she's on the clinical side, he's on the research side. So it's going to be a super cool talk or opportunity to hear kind of what they do. And they are, especially him, he is recruiting graduate students. All the people that are coming here that have graduate labs are kind of recruiting graduate students in the long term, or undergraduates that might want to work in the summer, those kinds of things. So keep in mind, everyone that comes here to talk is an opportunity to either just learn about what's happening at the cutting edge of science or to actually participate. So that's 4 to 5:30, and we do have food being prepared by our amazing, one of your fellow students, Erin Beeman. She is making chicken barbecue and vegan barbecue stuff. So there's going to be some cool stuff available. Logistics, any questions? We had 2 people go to supplemental instruction on Saturday. I appreciate those 2 people went, but not the best use of resources, so I will be trying to figure out a way to maximize utilization of that as a resource. Sure, go ahead.
Okay. If any of you are available on Thursday or Friday this week, the Girls of Promise initiative done by the Women's Foundation of Arkansas is really in need of volunteers. We're really short. So if you could do both days, I would love to have you as a team leader. All you have to do is work with the girls and talk to me. It's the easiest job you probably do. But if you just want to like take pictures or you want to get to know some of the really cool speakers that'll be there, you can be a speaker's assistant, but help's needed. If you're interested, let me know.
Can it be a male or female,
Yes.
or is it only female?
Male or female.
Great.
Males, you just won't get to be a team leader with the girls, because that was the one. They're grade 8 girls. I don't know if you really want to hang around them for 48 hours.
You're selling this really well. All right, thanks a lot for doing that. I appreciate it. All right, so what we're going to do today in class is we're going to unpack some of the stuff that you did in your pre-class quiz. And to do that, we're starting super simple. So I want you to look at the 4 compounds that are listed in question 1, and I want you to think about what do they break into when they dissolve in water. So go ahead and fill in those 4 compounds. What does it become when they dissolve in water? And then once you've done that, we're going to kind of step through them here one at a time. And I can only have you, it's easier to click in one of the 2, I guess. Can we do both? Is it hard to do both? Yeah, let's enter both cation and anion. Is that fair? So if you've already entered, please modify it. So I said just anion, but do both cation and anion. You write down both the cation and
Oh, yes.
it's because your phone's too small.
Dang.
That's why I have this thing. Alright, so let's go ahead and talk through these one at a time. We're going to dig deeper into all of them as the class goes on, but we're kind of superficial level right now. So if we split these up, let's take a look at actually what you guys entered. How about that? This is the problem, is that everyone does slightly differently, then it's all... Only those people got it right. I'm just kidding. All right, it looks like for the most part, some people were starting, like this answer here, you're starting to think about the next step, which we're not there yet. So all I wanted us to think about for this problem was, one, do you know your polyatomic ions? What is ammonium, NH4+? Iodide is an I with a minus. Remember, I means a negative charge. A little bit later in class, we're going to say, well, what pH is that solution going to have based off of those elements that are dissolved in solution? All right, so go ahead and enter for potassium nitrate. What are your ions that are formed? And at least our internet's working today. Very important part of that. Let's use the same formatting. Let's do cation, space, anion. If you haven't done that yet. All right, we're getting 61% people that are on board. All right. So we have a potassium ion, a K+, and an NO3-. Let's go ahead and do the next one. Cation, space, anion, please. How many people are looking up what these anions or cations are? If you find yourself doing that, let me not call you out. If you find yourself doing that, fair. On the common polyatomics, then I want you to go back and make sure that you know all of them by heart. Because this is going to build into what I would use for an exam question, so knowing this level is going to be important. All right, looks like everyone's in. Some people love them some brackets. Got one vote with brackets and commas. All right. So this seems like a really simple exercise, I'm guessing, seems like you guys are pretty comfortable with it. Don't forget the simple exercise when we start to do harder problems. This is the first step. Anytime you take a salt and you put it in water, you're going to say, where are the ionic bonds? I'm going to take those ionic bonds and I'm going to separate them. That doesn't mean that you're going to take the C and the N and separate those. Why not?
It's a polyatomic ion.
It's a polyatomic ion. Great, nice interpretation. Which means that there's covalent bonds there. Those covalent bonds might be polar, but they're not fully ionic. I'm going to get myself in trouble there because then we're going to start talking about acids and why acids are covalent bonds that then separate into water. But we'll get there. So the last one, we talked about this at the very end of last class. What is the important characteristic of that name that tells you this is a salt? There's two important things. Talk to your neighbor. What are the two characteristics of this name that tell you it's a salt? And that something will dissociate when it dissolves in water. Perfect. So can I hear one of them from a new volunteer? Let's try to get lots of voices today. What's one of them? Shanidra, looks like you want to volunteer one of them that your group discussed. Why? What is chloride? Cl minus. All right, the ide, remember, tells you it's a negatively charged species. Bromide, chloride, fluoride, iodide, all of those are negatively charged. So if it was not negatively charged, it would be chloro something, something, whatever. So that tells you that it's part of a salt, most likely, because it's negatively charged Cl. What's the other one? The other component? Angel? Why? What does ammonium tell us? What about it? Is ammonium in a name always mean it's this? No, this one's not, right? Dimethyl. Methyl is single carbon. So that's CH3. So this is CH3. Di means that there's two of them. And then it's ammonium. So what does that ammonium tell us? It's nitrogen. And then what's special about that nitrogen? Actually has nothing to do with hydrogen on it. It may or may not have hydrogens. What does ammonium mean? No lone pairs, which then means it's a positive charge. So if it has no lone pairs and it's a positive charge, how many bonds does it have? Nitrogen usually has how many bonds with a lone pair? 3. So if that lone pair is now tied up in a bond, it has 4 bonds. So this is a great example, right? N positive charge has 4 bonds. Those are all hydrogens. Dimethyl, 2 methyl groups. So what else is likely attached to that nitrogen? 2 hydrogens, giving it 4 bonds total. All right. Hopefully you're thinking, well, a nitrogen with a positive charge, I've seen that in a couple of my homework assignments. When that goes in water, does that act as an acid or a base? All right, so we're going to get back to that in just a second. That's what I want you guys thinking about, okay? So that's why we went through all of these. But before you can ask that question, if you didn't know that this was the compound and that it had a Cl minus and it formed a salt, you're going to be even more confused. All right? So the first thing is detangle the name, figure out what your cation and your anion are. Once you have that, say that those are going to dissolve in water. And then we need to decide what's going to happen with pH. All right, so my objectives for you guys today is to be able to identify conjugate acid-base pair and specifically determine the pH of a salt in solution. So that means that looking at the salts that we had, identify, is this the conjugate acid or the conjugate base of a compound that I know is a weak acid or a weak base, and therefore determine whether we think that's going to release protons and be an acid or accept protons and be a base. And then we're going to start talking about the common ion effect. What's going to happen if we add product or a reactant at equilibrium? So that's Le Chatelier's principle, but it's also the common ion effect that we've talked about a little bit. Hopefully, we're going to get to the fact of talking about an acid or a base. And then we're going to start talking about buffers. You guys worked with buffers in the lab, right? So this should be really easy, straightforward. All right. So this is the last question that I asked you guys in class on Wednesday. Talk to your neighbor now, answer this question, and try to justify why it has the answer that you're going to give it. And if you can't justify it, raise your hand and have one of us come around and help. Based off the answers, you guys don't look super confident. Even in the answer, even though that was the last thing we did, right, is I clicked on the right answer. So then talk to people around you. Try to figure out what the pH of the solution is going to be and why. What are the steps you do? Think about what we just talked about.
I just remember it was
All right, you guys ready to look at the questions and answers? Pretty confident in your answer? Even though we literally answered this question last class, I think there is more than 2/3 of the people in class. So, the question now is, why is that the answer? So what are the steps we would take? Judging off of what I started off class doing, what's the first thing we're going to do? Let's break apart any ionic compound and separate it into the components. And then we're going to ask, how does each one of those influence the pH? Sound fair? So we already talked about taking dimethyl ammonium, right? So a total of 4 bonds to that nitrogen means it has a positive charge, chloride. We're going to dissolve it in water, and when we do, we get the 2 ions. Then we're going to say, how does each one of those influence the pH? So I want you to talk to your neighbor in a small group. I want you to try to decide, is this going to act as a proton donor or proton acceptor with water? Is this going to act as a proton donor or proton acceptor with water? I want you to go ahead and come up with a concrete answer and justify why that is, thinking about conjugate acid-base pairs. And you have 4 or 5 of us walking around to help, so please raise your hand if you are kind of getting stuck.
It'll become an H3. It's a very common thing.
Can we bring it together? All right, so there's a lot of discussion. I'm not sure how much of it's focused on this. So let's talk through the individual components, and then you can follow up the question. Is that cool? So what I want you guys to do, or what I was asking for you to do, and hopefully it'll be kind of more straightforward in the next few of them, is let's take each one of the ions that's aqueous now and see, is this going to act as an acid, a base, or neither? So basically what I would do to answer that question is I'm going to write out Cl-. Okay, I'm going to be lazy and I'm not going to write aqueous because all the things we're going to do underneath here are aqueous. So if this reacts with water, can it donate a proton to water? No, it doesn't have any hydrogens. It can't do that. So we would say, well, let me write it out as a base and see what that looks like. How does that look? Why does that look super terrible? Colin?
HCl's are really strong.
So then what's wrong about how it's written up here? What should I change about this expression? Doesn't happen, right? That forward reaction does not happen. That's like taking table salt, putting it in water, and generating hydroxide and HCl. Come on. So what we're going to notice is that if our products are weak acids or weak bases, then yeah, we can describe that as Kb, and that's okay. But if we're saying that chloride is a strong enough base to tear a proton from water, leaving you with a hydroxide and a strong acid, then we're missing the whole point of what a strong acid is. You're never going to have these two in the presence of each other, first of all. Second of all, you're never going to have this on one side of an equilibrium arrow because it's going to be a full reaction the other direction. Okay? So that has no influence on the pH. That's just what we say. It doesn't make it more acidic. It doesn't make it more basic. It makes it neither. So then let's take a look at the second half of it. So, is this going to act as an acid, a base, or neither? So Josh, why do you think it might act as an acid? Oh, I messed up, didn't I?
That makes sense, that's why, to me. I don't know why it would, but it made sense.
So is this Ka or Kb that I just wrote out? Donating a proton from something to water, that's our Ka expression. Does that look good? Look bad? What do you guys think?
Fine with it.
You need to be able to differentiate whether this looks reasonable or not. That's what your goal is at today's class. So, does this nitrogen have a lone pair here? It has a positive charge. It has 1, 2, 3, 4 bonds. That nitrogen does not have a lone pair. Hopefully one of the trends you're starting to see is that if a nitrogen has a lone pair, it can act as a weak base. Because that lone pair, a nitrogen, I'm going to draw just 3 bonds to it. That lone pair is what gives nitrogen its basic properties. Because if there's an H plus floating around, the definition of a base is it can accept an H plus, right? It takes these electrons and makes a bond with that hydrogen. That's the covalent bond afterwards. If it doesn't have that lone pair, it can't make a covalent bond with an H plus because it has no electrons to make that bond. So, no lone pairs, can't be a base. Are there any other nitrogens here that can accept Or an O minus maybe that can accept a proton. It's nothing else. So there's no way that this can act as a base, but it can donate a proton, and then over here, once we write that compound out and take away one of the H pluses, we notice the nitrogen is now not positively charged anymore because it only has 3 bonds, which means it has its lone pair, which means that that's the conjugate base, and it actually is a weak base. Are nitrogens ever going to be, in this class, strong bases? What makes a strong base? What do the strong bases have in common in our class? With some sort of metal. All right, sodium, potassium, calcium, lithium. What's that? Strontium. All right, so nitrogens in this class are never strong bases. In organic chemistry, we do some weird things, and you'll get nitrogens that are strong bases. But for now, you're always going to say weak base with a lone pair. Nitrogen, lone pair, weak base. All right? So then overall, go ahead, Josh.
Does the value of molarity have an impact on this equation overall? If you had put 10 or 1,000 or you had 0.1, what does that?
If it was 0.00001,
Not really.
then you would say it's a pH of 7. So if it's extremely dilute, then you basically say that pH is neutral. But otherwise, it's going to be whatever the overall effect is. So now we say we have something that can act as an acid. We have a Ka that can describe it. If I gave you guys Kb for this compound, could you find the pH of the solution? If you have Ka, can you find the pH? How? So we'd use an ice table, but what would we need to do before the ice table?
Divide by 1.0 or numerator 1.0 times everything is 14.
Okay, so we would need to find, if I gave you Kb, you'd need to find Ka. You would use that to describe this reaction and try to find your concentration of H3O plus at equilibrium. All right. Feel good about that? So we could write out our Ka. If we had Kb, we could calculate Ka, and then we could do a nice table. So what I want us thinking about now is if we had some dimethylamine in water, right? So now we're doing the amine, not the ammonium. This is building off what we did in the class on Wednesday. You guys remember what the pH was of this solution? Does anyone still have those numbers? Did we calculate those numbers? Or was this what we did like super fast at the end of class? All right. Let's go ahead and figure out what the pH is of the solution at the top of this problem, right? All right, I've highlighted the question I want you guys to click on your answer to. Please solicit help if you're getting stuck with the group around.
Don't take it anymore. What do you ask for?
That's why
I got
Hey guys. I definitely this is so right away, so which I guess region
I mean, it should be amazing.
so what I would do is I would do the right situation, right, where so all I would do is 1.5 take the square root of that. And then if you do the negative log of that, then subtract 14 minus whatever that is. What do you get? That sounds right. I got a little bit of a different number, but I can have a calculator. Yeah, it happens. That's exactly
Right, but you don't know the actual. You said you have to take the square root of it. Like, who do you do? And so I'm gonna try to do oh, did you do the square root?
More seconds. right, before we start to do any calculations, what's the first thing you do? No equations, no plugging in, no nothing. First thing you do. What's that, Logan? Guesstimate. Do we have an acid in water? Do we have a base in water? Do we have a salt that we need to figure out if it's an acid or base? Which one do we have? Salt. We have a base because there's a nitrogen with 3 bonds. That means it has a lone pair. It's a base. So what's the pH going to be? Basic. Greater than 7. As long as it's 25 degrees Celsius. Did you get an answer that was less than 7? If so, you might need to think about some of the steps. You might have missed a step somewhere. All right? So let's walk through the steps. Let's work through it together. Kayla. Thank you. Trying to get everyone together so we can work through this. We still got a lot to do today. All right. So how, now that we know it's going to be a pH of 7, that helps guide us once we get our answer. If we have an answer that's like 3 or 2, we know we're wrong. So what steps do we do now? Balanced equation, because we have a weak base in water. So we're going to say, I'm going to simplify. Base, lone pair, plus water, yields, base, protonated, no lone pair, plus OH minus. Is that Ka or Kb? Kb. Okay, so we wrote out Kb there. Right, so nitrogen, 3 bonds, lone pair. That's what defines it in this case as being a base. Or it can be something with an O minus. That's also something as a base. So then if we write out, we have our equation now, what do we do? Perfect. So that's our reaction. We have initial, change, equilibrium. What's our initial concentration of all those guys? 1.050 molar. We don't care about water because it's an excess. Do we have any of the products? Is this actually 0 over here? Hopefully if you did activity 44, you look at the table. There is 1 times 10 to the negative 7th molar of OH minus concentration in water. But that's going to be so small compared to these values that we're essentially going to call that 0, but I'm going to put that in quotations. Okay? And then we're going to have some amount of that being used up, being produced, because Q is less than K. I always want us thinking about Q and K. And then we have 1.50 minus x, x, x. And our Kb is written up there as well. So then, actually if I use that space, what are the values that I plug in for all of these up top? X squared over, but can we approximate? I think we're going to approximate. All right? And here's where I think most people probably go wrong. So you go ahead and you solve for x. What is our x value? Ten to the what? What is x, Josh? What is this number representing? What are the units on it, first of all? And then what is it? Austin, you want to help out?
Change in concentration.
It's the change in concentration of our initial base. But how does that help us, or what version of x helps us solve this problem?
I mean, it gives us our hydroxide atom.
This is the part of the ice table that helps us solve this problem. What happens if we take the negative log of x? Isn't that pH? Okay, so this is where it's really important that you write out the ICE table, see what your X value is representing, and then making sure that if we take the negative log of that, one of the easy ways to check ourselves there is if we have a pH that's on the other side of 7 than we'd expect. Right? If we expect it to be acidic and it's greater than 7, then that should be a telltale that we probably just forgot that this was OH minus and not H plus ion concentration. And the last thing I'd want to add is molarity to that. So then, how do we find the pH? So I hear 14. What about 14? So we could find the POH. The negative log of that, which gives us what? 1.53? Is that enough sig figs? Wait, what did you guys get for the POH? Is this the number?
Yeah, I get 1.5.
Should it be 2.6, 5.26, or 5.3?
I thought it was
3 sig figs, 3 sig figs, 3 past the decimal.
What do we have to consider for
KB can always be looked up as a more accurate value, so I would not use KA or KB to determine the accuracy of your value. And then the last step, 14 minus POH equals pH. Is there another way we could have found pH once we had X? How?
That would be your take KW divided by the concentration of OH and you get the concentration of H plus.
Great, so pause. So we know that KW equals the concentration of OH minus times the concentration of H3O plus or H plus. Remember, I'm using those interchangeably. So if we know OH minus concentration, we can find H3O plus concentration through KW. Either one of those two approaches will give you the same answer. And then we can take the negative log of the H3O plus concentration and find pH. All right, any questions? Can you guys do that on your own? So what you're going to be expected to do on the exam is I give you a compound. You need to decide, is that an acid or a base? I'll give you either a Ka or a Kb, and that may be something you need to find the opposite of that in order to answer the question. You need to figure out, is that going to require me writing out the Kb equation or the Ka equation, and then you determine which one you need. And then figuring out what is your X, what does that mean, how do we use that to answer the question. So, with all of that said, what would happen to this pH? What did we determine it was? 12.473. What's going to happen to that pH if we add to that solution dimethyl ammonium chloride? So go ahead and pick which one of those three is going to be a true statement about the pH. We add dimethyl ammonium chloride to that 1.50 molar solution of dimethyl ammonia, or amine.
But that's not the same thing. This is CHC.
Yeah, I'm talking about no, that's not.
Couple more seconds. All right, we're split on this question. I want an answer based on just the simplest of logic, not using any equations or any math or anything. What's going to happen to the pH of this solution of dimethylamine when we add dimethyl ammonium chloride to it? Love?
It's going to go down
Why?
because you're increasing the amount of the dimethyl ammonium, which is plus. And if you increase the amount of those products, it's going to do a left shift.
So you're thinking about equations a little bit too much. Let's back it off one level from that. We add dimethyl ammonium chloride. Well, no, not even that. We're just adding an acid. We decided just a second ago that dimethyl ammonium chloride, when it goes in water, acts as an acid. It donates a proton. Done. That gives you your first answer. The pH will go down. All right. Now I want us thinking about why that is. So let's go ahead and answer the second part of that question. What's going to happen to the Kb? And I have the Kb expression written right here. And we're adding dimethyl ammonium.
2 more dimethyl ammonium?
No, it's the same, right? We have the solution at pH of 12 point whatever we decided. To that, we're adding dimethyl ammonium chloride.
Is that H2O? This solution? You're adding something that wasn't already there, right?
All right, a couple more seconds. Get your answers clicked in.
I'm going to find out.
All right, so we don't have an answer to this. I want you I heard a couple of key phrases throughout the class. What is the key point that will help us answer this question? Avery, can I have you share your group's discussion?
I had said that KB was a constant because we can look it up on a table no matter what we're being given.
All right, so pause. So what does that mean? So if KB is a constant and it doesn't change when you change the concentrations, what is changing? What's that?
Q.
You guys remember that Q thing that we talked about a couple weeks ago? Right, that's what the concentrations are right now. What does that change look like? At some point then, we had our K, right? We had all of these that were in the right exact orientation and relative values to give us this KB. That's what we calculated, right? We calculated X, which was each of these concentrations, and this is pretty much still 1.50 molar. But then if one of these goes up, right, we're basically adding this. Now our Q is different from our K. So we're no longer at equilibrium. Is our Q going to be bigger than K, less than K? Which one is it going to be? Increase this number only to start with. We increase the numerator, that means the number is going to be bigger, so our Q value is now bigger than our K value. So that means that while our K doesn't change, our Q value does. And then we have to say, well, what happens in order to get back to equilibrium? If our Q is bigger than our K, how are we going to take this reaction and force it to go back to equilibrium? Does the reaction proceed in the forward direction to get to equilibrium, or does it go in the reverse direction? We're going to have to make the top smaller because our Q got bigger than K. We're going to have to take some of these, use them up, and produce this. All right? That's called the Chatelier's principle. It's really that simple. The Chatelier's principle says if you have a system at equilibrium, and then you change something in it, you change your Q, then to way oversimplify, I don't even know oversimplify, to state it as accurately as I can, Q always goes back to K. So if you can just figure out what the change in Q was, then you don't need to worry about all this mumbo jumbo about Le Chatelier's. It just says that your reaction is going to always make Q go back to K. You just have to figure out what has to change in order to get there. So let's take a look at this reaction here. This is the Haber process. This is one of the biggest revels in modern science. This was the way in which we now produce our ammonia, which is fertilizer that's used over the entire planet. Before we had that, the amount of crops we could grow on the planet were limited to the amount that bacteria could make from decomposing matter. We don't have to worry about bacteria anymore. We can make as much ammonia and fertilizer as we want. So, in theory, the Earth has limitless potential to make food for us because we can now artificially make our own fertilizer. So, using this definition, this is kind of our Le Chatelier's, right? An external stress is applied to a system at equilibrium. The system adjusts in a way that stress is partially offset. And I actually hate. What might people come to a conclusion of inappropriately by that wording?
K would change.
That your K changes. So I think I might have even added the same K at the end there. Because a lot of times people are like, the equilibrium shifts to the left, or it shifts, the equilibrium shifts to the right. The equilibrium doesn't shift, right? Q shifts to K. But K is going to be a constant in all these examples we're talking about. So, if we have this reaction at equilibrium, and it's stabilized, right? The reaction forward direction is the same rate as the reverse reaction. If we're there, and then we add some ammonia, what's going to happen to Q? Is Q going to stay the same or change if we add products when it already had reached equilibrium? Q got bigger than K. So what's going to happen to get this reaction back to equilibrium? All right. And so the terminology I'm going to use is the reaction shifts, or the reaction proceeds to the left to reach equilibrium again. I really don't like equilibrium shift terminology. I think it's terrible. So let's go ahead and think through an example of this. I think I have these numbers printed out on your sheet. So if we have those initial those concentrations, the reaction, we find this reaction at equilibrium, I want you to go ahead and click in what your equilibrium constant for this reaction is. All right, this is question... Oh, there's no number? This is pre-question 5. You guess? Oh, it is 4. Yeah. All right.
It's just mine.
answer, please check with someone because the numbers I've seen so far are all over the place. All right.
You're not very sad.
No. So, how long should this question take us?
Not very long.
So I'm not sure where you guys are getting caught up. Can I get some feedback? Where are you guys getting hung up? So on your paper, there's something missing. What's missing on your paper?
The balance.
Stoichiometric coefficients. Did you guys balance your equations?
Yes.
So you always have to balance your equations. And then our equilibrium constant is concentration of products at equilibrium raised to stoichiometric coefficients divided by concentration of reactants at equilibrium raised to stoichiometric coefficients. So what value do we find if we go and calculate that? How many sig figs should we have? Which is this 2 sig figs? That was 2. 2 past the decimal.
This is just concentration, right?
I got in the wrong mindset.
No.
Thank you for catching that. All right, so we have an equilibrium constant. It's 4.1? So then we're going to say, we're going to add some hydrogen gas to the mixture, right? These are the concentrations we have at equilibrium, which are the numbers we used. And after we add some hydrogen, we go from 0.82 all the way up to 1.00 molar. You notice how these two didn't change yet. We're saying as soon as you make the change, we now have a different mixture. So then after we do that initial addition, and we're right here in time, what's going to happen to the concentration of hydrogen? Go ahead and click in your response. Is it going to go up from that point in time? Is it going to go down? Or is it not going to change? From this instant in time, as soon as we just added it.
From that instant to like
You're saying that concentration of H2 is what we have, that's what we have.
Yep. So you can't really see here, as there is actually a blue line. So these two are at equilibrium. This one we just injected some hydrogen gas. What's going to happen? Just to be 100% clear, when we're at these concentrations, and then we look 10 seconds later, what's going to happen to the concentration of H2? And I want to hear why. All right, we're closing out. So can I hear from 1v3 ladies? Marina, Chelsea, Danielle. What do you think is going to happen with the concentration of H+? We just jacked it up, right? We just went from 0.82 to 1.0 molar in that container. They're in a sealed vessel. What's going to happen to that concentration if we were to look a little bit in the future? Is it going to be a higher concentration of H2, a lower concentration, or is it going to be the same? Why would it be lower?
Because it's an equilibrium, so it has to shift to adjust.
So you said it is at equilibrium or it's not at equilibrium? It is here. So it was at equilibrium. Then we pushed it out of equilibrium. Kalia, what did you say about this right here? I heard you say something at the very last minute about why this reaction is going to proceed the way it is.
Oh, Q is less than K.
All right. You guys see where she's getting that from? If you recalculate Q, this is on the denominator, so it's going to be a bigger value, but all the other numbers stay the same. So your Q is less than K, which means that in order for the reaction to get to equilibrium, we're going to have a decrease in the concentration of the thing that's now out of whack. Humphrey? Can you say it a bit louder? So we're going to get there. Good question. So that means that the concentration of H2 is going to have to go down. So then exactly Humphrey's question, what's going to happen to the concentration of N2? Go ahead and click in your response. In order to get back to equilibrium, as Danielle was saying, what has to happen? A couple more seconds.
Are you saying concentration of the species that is increasing? Okay, so for example, for your H2, the concentration of H2, what will happen? Oh, never mind, I answered my own question.
All right, you guys look super confident in this one. Actually, you became more confident, so there was a shift over time. How? We said the concentration of hydrogen gas has to go down to get back to equilibrium, right? Because Q is less than K. This shot up. Can someone tell me how that concentration of H2 goes down?
By converting into NH3.
A little bit louder, Sam?
By converting into NH3.
What do we need to convert H2 into NH3? Josh? We need N2. We need to use up N2 to use the H2. Without both of those, we can't use either of them. All right? So I agree with where the majority of the class ended up, that we have to use both of them in order to get to equilibrium. So then last question, 10 seconds. What happens to the concentration of NH3? Closing out. 44. You good, Mode?
I'm good.
All right. I agree. All right, so let's take a look at what that means graphically. So if we throw a reaction out of equilibrium, we change Q right here, then in order for Q to get back to K, we have to convert reactants to products. Reactants were used up, product was made through the stoichiometry. That's Le Chatelier's principle, right? That's how we figure it out. So if you wanted to calculate that, what would the new equilibrium be? Then you could just think about how much of one is used, how much of the other is used. You could use an ice table. It's a little bit complicated, but we could work through that. And I think we'll be doing that type of stuff here in a little bit. So let's do this briefly. We're going to do this really quick. You guys focused? Super focused? Because there's one thing I need to get to after this. All right? We have a reaction, right? Stupid generic reaction. We have this stuff here. I want to know if we increase the concentration of C, right at that second when C concentration was higher than equilibrium. So we started at equilibrium, and then we're going to add some C. Which way is the reaction going to proceed in order for Q to get back to K? Is it going to proceed to the right, to the left, or is it not going to change? Do you need clarity on what I'm asking? All right, couple more seconds. Looks like we got everybody in. Almost everybody says to the left. Why? Talking the Q versus K argument, why is this reaction going to proceed to the left? Q ended up bigger than K. So then in order for the reaction to equilibrate, we have to use up both C and D, because we can't use just one of them. It doesn't work like that. Great. All right, what about if we decrease the concentration of D? Which way is the reaction going to proceed to reach equilibrium again? I mean, I kind of had questions in this vein on the test. I expect a lot of you guys. All right. So if we remove products, you want to hear something really cool? That equation that we were just talking about, the Haber process, that equation actually has a really, really, really terrible K value, even if you heat it up a lot. The K value is like, it's actually like 0.25 or something like that. It like barely creates any of that NH3 gas that we want. So one of the ways, because NH3 is a product, and we have H2 and N2 over here, remember? One of the ways to get that reaction to make more product is you do it really hot where everything's a gas, you cool it down. Which of those three turns into liquid first, based on your knowledge of intermolecular forces? N2, H2, or NH3? NH3 can have hydrogen bonding between molecules, so it turns into liquid. So you have this gas container, you cool it down, you have a liquid come out. Turn a pour spout, ammonia pours out the bottom. Close it, heat it back up again. The reaction goes again. We just removed some of the product, drove the reaction forward. It's kind of cool, right? Actually works like that. All right, if we increase the concentration of B, which way is the reaction going to have to proceed in order to get Q back to K? Couple seconds. What's that? Closing out. I agree with the majority of the class. Increase the reactance. That means Q is smaller than K. We're going to drive the reaction forward. And you guys could do this one, right? All right. So now let's go back to where we started in class. And we can kind of think about this with the Chateliers in the background as well. We started out slide number 1 with this part of this question. So I want you to go back and think about that, and then think about which of these answers would be most appropriate.
So you do K, C, plus because we're adding one.
Go ahead, let's do it.
a couple more seconds. Looks like we're not 100% sure. Can I get someone to talk me through the process? Matt?
We can start by writing out the equation.
Okay, what's the equation?
Well, we have KCN plus H2O can form HCN.
Skipping a step.
Okay.
Is that what I had you do in the homework?
Yes.
Okay. So I'm going to have you do it as 2 separate steps.
Okay.
So write the 2 different.
All right. So like we did in the very beginning of class, whenever you see a salt, separate it first. And then you ask yourself, can either one of them accept or donate a proton from water? K plus. What's that going to look like? Is that going to be an acid, a base, or neither? K plus doesn't have a proton to give. If you accept a proton, it's going to be KH2 plus. Doesn't make any sense. All right. So then the question does not become automatically, oh, so CN, because it doesn't have a proton, is a base. The question is it a base? We have to ask that separate. Can that accept a proton from water? So I always say go ahead and write out your expression for Ka to determine that. What would my product be in this case if I'm describing Ka? So on every exam from now on out, I think I will give you a table of weak acids and their Ka values, and some weak bases and their Kb values, just like you have as references in your homework. So you would go to your table and see, does this thing have a Ka that says it's a weak acid? Did anyone Google it? So in class, if you don't know, you could Google it and say, yes, it has a Ka that's reasonable or not. I think the Ka is like 1 times 10 to the negative 5th or something like that. So then the question is it weak or strong? Like Love was saying, if it's not one of the 6 strong acids, you know that it is not a strong acid. So this is a weak acid. So then what does that tell you? How does that help us answer this question? Angel? The HCN would not dissociate very much. What does that tell you about the pH of the potassium cyanide solution? Is it acidic or basic? This right here was describing Kb. CN acts as a base. That's what we described. If you find, because it's the conjugate base of a weak acid. So we're looking for what does K plus do? What does Cn minus do? Cn minus accepts a proton, so that means it's a base. It's a base. It means that our pH is going to be greater than 7. Did you guys do the other two? Ammonium iodide. Can we do these two quick? Yes. We're not doing this again next class. Ammonium iodide. Greater or less than equal to 7. Let's do a couple more seconds. Majority of the class is answering C on this one. Why? Love? We have NH4 plus. What about question 10? Did you guys do that one? 10? Was it KNO3? What do you guys think? Acidic, basic, neutral?
Neutral.
You should recognize that if this accepts a proton, you have that. And if you know your 6 strong acids, this is a strong acid. All right. When I go back to my office tonight, I'll put up the pre-class quiz for Wednesday. It's going to be about this and starting thinking about buffers. And we will see you guys on Wednesday.